Welcome to the deep dive. Today, we're plunging into the fascinating world of pterodynamics
Right.
and their, well, pretty ingenious transwing VTOL drone technology. That's vertical takeoff and landing, of course.
Yeah, it's a really interesting approach they're taking.
We've got a detailed analysis report on Terodynamics, plus the specs for their different drone prototypes. So our mission today is really to get under the hood of this tech, understand the core ideas, the benefits, the potential downsides
Without
too,
downsides, yeah.
and see how they kind of stack up against the competition. And we're also going to dig into why they chose that turbo generator for their big heavy lift model.
That's a key part of it, definitely.
Yeah.
What's really compelling, I think, is how PteroDynamics is trying to crack that classic problem.
Right.
How do you get helicopter-like agility for takeoff and landing, but also fixed-wing efficiency for, flying long distances, all in one autonomous package?
Exactly. And their transwing technology is supposedly their answer.
That's the idea.
Okay, so let's unpack this. Terodynamics. What's their specific angle? I mean, the drone space is pretty crowded, right?
It really is. But PteroDynamics, their focus is specifically on these autonomous VTOL fixed-wing systems. And the big differentiator is that patented transwing platform.
The folding wing.
Yeah, the folding wing design. It's basically an attempt to engineer the best of both worlds.
So you get the VTOL maneuverability for tricky spots, like landing on a ship or something.
Exactly.
But then once it's up, it transforms into a regular plane for speed and range.
That's precisely the goal. They want to merge these two kind of opposing capabilities seamlessly. The transwing actually lets the wings fold and unfold during flight.
In flight. Wow.
Yeah, which allows that transition between hovering, for vertical stuff and then a clean, streamlined shape for efficient horizontal flight. It's a pretty bold engineering approach.
Yeah.
Tackles a real long-standing trade-off.
Okay, folding wings in flight. That sounds mechanically complex, to say the least.
Oh, definitely.
So what kind of real-world problems are they actually hoping this solves? What are the target applications?
Well, the report points to mission-critical roles, both civilian and government. Think about time-sensitive deliveries, like medical supplies to remote places with no runways.
Ah, okay. Makes sense.
That's a key target. Specific examples mentioned are things like maritime logistics, moving cargo autonomously over long distances, infrastructure inspection like pipelines or power lines.
ISR?
Yep. Intelligence, surveillance, reconnaissance, ISR, and public safety uses too. Basically, anywhere VTOL capability or long endurance is really valuable. Terodynamics is trying to offer both in one package.
And it seems they're not just tinkering around, they're working with some pretty serious players, right?
Absolutely.
Yep.
Their work with the US Navy on the Blue Water UAS program. That's all about solving ship-to-ship resupply challenges at sea. That's a big indicator of the need.
Definitely.
Plus, they're collaborating with Leidos on DARPA's Ancillary project.
Right, I saw that. Ancillary is pushing the envelope on advanced VTOL aircraft.
Exactly. So that collaboration further validates their approach. It suggests they're serious about moving this beyond just prototypes and into actual use.
Okay, so that paints a good picture of who they are and the big challenge they're tackling. Now, let's dive into these drone prototypes themselves. What are the core advantages Terodynamics claims for this transwing tech? And, what are the potential headaches, the challenges?
Okay, let's start with the potential wins.
Yeah.
A major one they're banking on is better aerodynamic efficiency in cruise flight.
Right, because it flies like a normal plane then.
Exactly. It transitions to that clean, fixed-wing shape, so it avoids the drag and the weight penalty you get with, say, extra lift rotors that other VTOL designs might carry around.
And that translates directly to longer range, better endurance.
That's the idea. Longer range, greater endurance. They can even feather or fold the main propellers during cruise to cut drag even further. Really maximize that fixed-wing efficiency. It's pretty fundamental to their whole bet.
That makes intuitive sense. Less drag means better fuel economy or longer flight time if it's electric. What else?
Payload capacity efficiency is another potential benefit. If you're not carrying that dead weight from separate lift systems during cruise,
you can carry more payload or fuel.
Precisely. More payload or more fuel for longer missions within that same maximum takeoff weight. Faster cruise speeds are also a plus, again, thanks to that cleaner, streamlined design. And interestingly, the report mentions good stability during VTOL, even in gusty conditions, which is really critical for things like operating off ships at sea.
That smaller operational footprint seems like a big deal too, especially for remote operations.
Yeah, definitely a logistical bonus. The XP4, their smaller one, apparently needs less than 30 square feet to land. That's remarkably compact.
Tiny.
And those folding wings aren't just for the in-flight transition. They make storage and transport much easier, in tight spaces like on a ship or in a truck.
And full autonomy.
Yep. Designed for full autonomy, takeoff to landing, which reduces operator workload, potential for human error, all that.
So the core idea, just to reiterate, is using the same propellers for both lift and thrust just by reconfiguring the wings.
Exactly. It directly tackles that classic lift versus cruise problem that so many other VTOL designs struggle with.
Sounds great on paper. But you mentioned potential drawbacks. What are the big engineering hurdles and maybe reliability concerns?
Well, number one has to be the mechanical complexity of that folding and locking mechanism.
Right. More moving parts.
More moving parts means more potential failure points. It means potentially more maintenance, more complex maintenance, especially in harsh environments. Think saltwater spray, dust, icing.
Yeah, that could be tough.
The long-term durability of those mechanisms under constant stress from flight loads, vibrations, environmental factors, that's a huge engineering challenge they absolutely have to nail.
And what about that moment of transformation? When the wings are actually moving in midair? Sounds tricky. Aerodynamically.
You hit it exactly. That transition phase is aerodynamically very complex. You need incredibly sophisticated flight control software and reliable sensors to maintain stable, predictable control while the wings are articulating.
Risk of instability there.
There's an inherent risk, yes. They have to manage that very carefully. And, while they save weight by not having separate lift systems, the folding mechanism itself, the actuators, hinges, locks, all that adds weight.
Ah, right. So they have to make sure that added weight doesn't cancel out the savings.
Exactly. It's a careful balancing act.
And the structural integrity at those fold points must be critical too. They need to handle forces from both VTOL and high-speed flight.
Absolutely critical. Those joints have to be incredibly strong to handle the loads from high-thrust vertical maneuvers and the stresses of fast-forward flight, all without being excessively heavy.
And all this complexity probably means higher cost, right? Manufacturing, maintenance.
Potentially, yes. Higher initial manufacturing costs, possibly higher long-term maintenance costs seem likely, although Terodynamics is probably banking on the operational efficiencies like better range, more payload per flight, eventually offsetting those higher costs for the users who really need those capabilities.
Okay, let's get specific now. Let's look at the actual drone prototypes. First up, the XP4. What's the story with this one?
Right, the XP4, that's their smaller, fully electric folding wing UAV. It's really positioned for critical logistics, sort of shorter range stuff.
Specs.
It's got a 4-meter wingspan, electric powertrain, obviously. Max takeoff weight is 38 kilograms, about 84 pounds. Payload is up to 7 kilos, maybe even close to 12 kilos if they reduce the battery size a bit.
Okay. Speed, range.
Cruise speed is around 65 knots, dash speed up to 100 knots. Range is about 60 nautical miles with max payload, and endurance is roughly an hour under those same conditions.
Being all electric has its pluses, I imagine.
Oh, yeah. Runway independence, obviously. That's the whole point. Vertical takeoff and landing into tight spots. Electric means potentially faster deployment, simpler pre-flights maybe, lower noise, zero emissions during flight.
Good for stealthy or sensitive missions?
Could be, yeah. And that 100-knot dash speed is pretty decent for a smaller electric UAV. Good for getting somewhere quickly if needed.
But the electric nature also means limitations, right?
Absolutely. Range and endurance are inherently limited compared to fuel-burning aircraft. That payload, while okay for its size, might not be enough for every logistics task.
Weather dependency.
Smaller electric UAVs can be more sensitive to bad weather, strong winds. And then there's the whole battery logistics challenge, charging them, swapping them, especially out in the field.
Okay, moving up the scale. The XP5. This sounds like a bigger step up.
It is, yeah. The XP5 has a larger wingspan, 7 meters. And critically, it uses a hybrid powertrain, electric and combustion, specifically designed for JP5 fuel, which is common military jet fuel.
So bigger size, hybrid power. What about payload and performance?
Max takeoff weight jumps up significantly, around 145 kilograms,
Right.
or 330 pounds for one variant mentioned. Payload is a solid 23 kilograms, about 50 pounds. Cruise and dash speeds are actually similar to the XP4.
Oh, interesting.
But that hybrid system gives it dramatically longer reach. Range is quoted up to 1,200 nautical miles.
Wow, 1,200.
Yeah, and endurance up to 19 hours with max payload, plus a higher ceiling, 18,000 feet.
That hybrid powertrain really is a game changer for range and endurance then.
Totally. It opens up much longer missions,
Yeah.
long-range cargo, persistent ISR, that kind of thing. The extra payload capacity and higher altitude also add versatility. Can carry bigger sensors, operate more airspace.
Better fuel efficiency too, potentially, compared to just a gas engine.
Potentially, yes.
Yep.
A well-managed hybrid system can optimize engine use and often achieve better overall fuel economy.
But again, trade-offs. More complexity with hybrid, I assume.
That's fair. You've got both electric and combustion systems to manage, integrate, maintain. More potential points of failure.
Noise, fuel logistics.
Right. The combustion engine brings back an acoustic signature. And you need fuel logistics alongside the battery management. Plus, it's likely a more expensive aircraft to acquire initially.
All right, let's get to the heavy hitter, the XB7 heavy lift VTOL drone, turbo generator powered. That sounds advanced.
It definitely is. The XP7 is the flagship. Big step up again, 10-meter wingspan. Max takeoff weight is a hefty 1,360 kilograms, almost 3,000 pounds.
And the payload, that's the headline number, right?
Massive payload, 280 kilograms, which is over 600 pounds.
Whoa.
Yeah. Cruises fast too, 120 knots. Dashes over 180 knots. Range is still impressive, even with that huge payload, 1,000 nautical miles.
1,000 miles with 600 pounds. That's serious capability.
It is. Endurance is about 9 hours at max payload, same 18,000-foot ceiling as the XP5, but it also provides a significant 3 kilowatts of power for the payload itself.
Okay, those specs are genuinely impressive for a VTOL UAV. That payload opens up totally different missions, doesn't it?
Absolutely. Transporting really substantial cargo, deploying very large, complex sensor suites. The high speed and long range make it suitable for time-critical missions over vast distances.
Replacing manned aircraft in some roles, potentially.
That's the kind of capability level we're talking about.
Yeah.
And that turbo generator, which we'll get into, is what enables that kind of power density.
But that level of performance must come with significant trade-offs. Complexity, cost, operations.
You got it. The XP7 is undoubtedly a very complex machine. That means higher anticipated costs, both to buy and to maintain over its life.
Fuel consumption. Noise.
Turbo generators can be thirsty, and handling specialized aviation fuels is a factor. The noise and heat signature from a turbine are much higher than electric or piston engines, which matters for some missions.
Regulatory hurdles too, I bet, for something that big and powerful.
For sure. An unmanned aircraft of this scale will face intense regulatory scrutiny, and you'll need specialized expertise to operate and maintain it.
So the report included a table, right? Comparing these three side by side.
Yes, and it really highlights their strategy. You see the scaling of the core transwing design, but with different power systems tailored for different mission sets.
From the smaller electric XP4 for short hops,
Through the long-endurance hybrid XP5 for versatile roles.
all the way to the turbo generator XP7 for that extreme heavy lift, long-range performance.
Exactly. It's a tiered lineup trying to hit different segments of this growing VTOL UAS market.
Okay, let's shift gears now and look outwards. How does Terodynamics stack up against the competition? The report gives some clues there.
It does. I mean, the VTOL UAV market is booming. Lots of demand for versatile, efficient drones, and you've got established aerospace giants and nimble startups all innovating.
So who are the main competitors, the analysis points out?
It specifically mentions Quantum Systems, JOUAV, and EHang as key examples. And it also notes the big defense contractors are active here too.
Okay, let's take Quantum Systems first. What's their approach?
Quantum mainly uses tilt rotors or fixed wings with dedicated VTOL rotors, like their Trinity Pro or F90 Plus.
So separate systems for lift and cruise?
Generally, yes. Their aircraft tend to be smaller, lighter than Terodynamics' bigger models, really focused on data acquisition, mapping, surveying, that kind of thing.
Strengths.
Often known for ease of use, good mission software, flexible sensor integration cameras, LiDAR. But again, the transwing approach aims for better cruise efficiency by not carrying those extra VTOL rotors as dead weight.
Right. What about JOUAV? They seem to have a wider range of drones.
They do, yeah. JOUAV uses different designs like quad planes, fixed wing, plus vertical lift rotors, or dedicated lift plus cruise systems in their CW series.
From small electric to bigger hybrids.
Exactly. They have smaller electrics like the CW15 up to larger hybrids like the CW30E with really long flight times. Their upcoming CW80 looks like it might compete in a similar heavy payload class as the XP7, but probably using a different powertrain, maybe hybrid gas-electric, not turbo generator.
So again, mostly separate lift and cruise systems.
Typically, yes.
Yes.
Which is where transwing aims to be different, focusing on efficiency through that wing transformation.
And EHang, we mostly hear about their passenger drones, but they do cargo too.
They do. Their cargo drones, like the EH-216L, are mostly multi-rotor eVTOLs, big multicopters.
Payload.
They can actually lift quite a bit, sometimes comparable to the XP7's payload capacity.
But range must be the limitation there.
Big time. Being pure battery electric multi-rotors, their range and endurance are much, much shorter. They're really designed for short-hop urban logistics, kind of a different niche than Terodynamics' long-range focus.
The report mentioned other players briefly, too.
Yeah, it just touches on them. Harris Aerial does heavy-lift multi-rotors, often hybrids. Lockheed Martin's exploring things like rotor-blown wings. Northrop Grumman is in that DARPA ancillary program, too. Boeing has ScanEagle VTL and cargo eVTOLs. Airbus has various tactical UAS. It's a very busy space, lots of different ideas being tried.
So with all that competition, where does Terodynamics potentially have an edge? And where might they be at a disadvantage?
Well, competitors with simpler, maybe more proven VTOL mechanisms might have lower costs for certain capabilities. The big players have established support networks, software ecosystems, track records.
Niche specialists, too, like EHang for urban lift or quantum for mapping.
Right. But Terodynamics' potential ace is that theoretical cruise efficiency from the transwing design. If they can prove it works reliably and delivers significant real-world fuel or energy savings.
And prove the folding mechanism is durable.
Exactly. If they can demonstrate both the efficiency and the reliability, they could carve out a really valuable spot. But it's a tough market, and different solutions will likely win in different segments.
And that comparative table in the report helps put their performance targets in context, right?
Yeah, it shows where the XP4, XP5, and especially the XP7 fit in terms of payload, range, endurance, compared to what else is out there. The XP7's combo of heavy lift and long range, thanks to that turbo generator, really does stand out from most electric or smaller hybrid options.
Okay, let's circle back to that turbo generator then. Powering the XP7. What's the fundamental reason for going with such an advanced, maybe less common, power source for a drone?
It really boils down to one critical thing: the need for exceptionally high power density.
Power density, meaning lots of power for not much weight.
Exactly. To get the kind of performance they want from the XP7, lifting that heavy payload vertically, then cruising fast for a long time, you need a ton of power without adding excessive weight.
Okay, so break that down. How does a turbo generator actually work on a UAV like this?
Right, so it's essentially a series hybrid electric system. You have a small, high-performance gas turbine engine.
Like a mini jet engine.
Sort of, yeah.
Yeah.
But instead of producing thrust directly, it's coupled to an electric generator. The turbine spins the generator makes electricity.
And that electricity powers.
It's electric motors, which then spin the propellers for both lift and thrust. So the turbine's job is purely to generate electrical power on board. It's like a flying power plant.
Got it. So the turbine isn't mechanically linked to the propellers at all.
Correct. Key parts are the microturbine itself, running at super high RPMs, usually a gearbox to slow that down for the generator, then sophisticated power electronics to manage the electricity, convert AC to DC, control voltage, etc. Plus the fuel system, the engine control unit, the electric motors, and often a small buffer battery.
A battery buffer? For what?
Usually for starting the turbine initially, and also to help smooth out any quick changes in power demand, making the whole system more stable.
And how does this all work together during flight?
Okay, so typically the battery gives the juice to start the turbine spinning. Once the turbine's up to speed, it drives the generator, making AC power. Power electronics convert that to DC.
Which then goes to the motors.
Right. The DC power feeds the electric motors for lift or thrust, powers the avionics, the payload, and potentially recharges that buffer battery a bit. There's a smart power management system constantly juggling things.
Juggling what?
It regulates the turbine's output to precisely match what the motors and systems need at any given moment. Keeps the voltage stable, tries to run the turbine at its most efficient point, manages the battery. It's a complex control task to balance power generation and consumption.
Okay, now let's really dig into the why. Why specifically a turbo generator for the XT7? The report mentioned power density, reliability, and cost. Let's unpack those. Power density first. Why is it so critical here?
Well, think about lifting 1,360 kilograms vertically, including that 280 kilo payload. That takes immense thrust, immense power. And then you need sustained power for high-speed, long-range cruise.
And turbines are good at power for their weight.
Turbines are exceptional in terms of power-to-weight ratio compared to piston engines or batteries, especially when you need power for a long time. Plus, liquid fuels like Jet A pack way more energy per kilogram than batteries.
So batteries just wouldn't cut it for 9 hours with that payload.
The battery pack would be enormous, incredibly heavy, impractical. The turbogenerator basically lets them carry their energy source as dense liquid fuel and convert it to electricity on board, as needed. It's the most direct way to get that much power without prohibitive weight penalties, enabling those big payload, range, and speed numbers for the XP7.
Makes sense. What about reliability? Are turbines generally seen as more reliable for this kind of demanding job?
Generally, yes. Turbine engines, mechanically, tend to be very reliable. They have fewer moving parts than piston engines, smoother operation. They often have much longer times between overhauls TBOs. Some microturbine makers quote TBOs in the thousands of hours.
Which is huge for mission-critical stuff.
Exactly. High availability is key. Now, UAVs overall have had reliability challenges compared to manned aircraft, but the core turbine technology is mature and robust. The real challenge for Terodynamics is ensuring the reliability of the entire integrated system: the generator, the power electronics, the controls, the fuel system.
And the folding wing mechanism, too.
And the folding wing, absolutely. But by choosing a turbine core, they're starting with a fundamentally reliable power source and betting they can engineer the rest of the system and the airframe to match that reliability for high uptime.
Okay, last factor. Cost. The report hinted cost might be secondary to performance here.
That's often true for the target market's military, high-value commercial logistics. The unique capability is paramount. Turbogenerators are more expensive to buy initially than piston engines or batteries of similar power.
What about operating costs? Fuel? Maintenance?
Fuel consumption can be a factor. Small turbines aren't always super efficient at low power, though the hybrid setup lets them optimize the turbine's operating point. Maintenance? Well, the longer TBO can mean lower overall lifecycle costs if the aircraft flies a lot, but specialized turbine maintenance can be expensive.
So the value proposition is really about the unique capability.
Pretty much. If the XP7 can deliver 280 kilos over 1,000 nautical miles, VTOL, replacing maybe a manned helicopter or multiple smaller drones, that capability commands a premium. The users needing that will likely accept the higher costs. Plus, distributing power electrically can have some efficiency benefits and potentially lower maintenance on the motors themselves. So yeah, turbogenerator was likely chosen because the performance it enables is essential, and the cost is deemed acceptable for that performance.
And how does it stack up against other power options for something this big? The report compared it briefly.
Yeah, basically concluded that for the XP7's mission profile, batteries don't have the energy density for the range endurance needed with that payload. Hybrid piston electric would struggle to provide enough power for vertical lift and high speed without becoming too heavy itself.
What about a direct drive turbine, like a turboprop?
That's an option. But the turbogenerator offers more flexibility. You can place the generator somewhat independently of the propellers, distribute power electrically to multiple motors placed optimally for lift and thrust, which might integrate better with the whole transwing concept. So, bottom line, for the XP7 specific goals, heavy lift, long range, high speed, endurance, the turbogenerator currently looks like the most enabling technology available.
Okay, let's zoom out again. Looking at Terodynamics' whole portfolio and strategy, what are the main strengths and weaknesses that come through from this analysis?
Strengths. Definitely the innovative core transwing tech. That's their unique selling point. They've got a scalable line from XP4 up to XP7. The XP7 itself is a high-performance flagship targeting demanding missions, and their engagement with the Navy and DARPA is a big strength validation and market access. Plus, that clear focus on mission-critical applications. Weaknesses. Well, it's still a relatively new technology that needs full maturation and proving out. Managing the complexity of three quite different powertrains across the line could be challenging. The turbogenerator in the XP7 carries inherent risks around reliability and cost. The market is intensely competitive, and they'll need to build out support and maintenance infrastructure.
And looking at the wider market, what are the big opportunities and challenges ahead for them?
Opportunities are huge. Growing demand globally for runway-independent drones, defense modernization driving investment, potential to penetrate niche markets where transwing offers a real advantage, maybe expand into new applications later.
Challenges.
Big ones. Navigating complex regulations and certifications, especially for the larger drones. Staying cost competitive. Scaling up manufacturing reliably and with high quality. Cybersecurity for autonomous systems is always a concern. And the big one, proving that real-world, long-term reliability and durability, especially for the XP7's turbogenerator, across all sorts of tough operating conditions.
This has been really illuminating. Terodynamics is definitely pushing the envelope with Transwing, and that turbo generator choice for the XP7, it's a bold move, aiming for truly standout heavy lift capability.
Absolutely. Their whole approach tries to fundamentally solve that VTOL versus fixed-wing efficiency puzzle. The XP7 especially is a big bet on achieving something pretty unique in the VTOL UAV space. But, as we've discussed, they've got some significant technological hurdles and cost factors to manage to make it a full success. In such a crowded market, they really need to deliver on the promised benefits and prove the reliability of their unique designs.
So it leaves you wondering, doesn't it? Thinking about those trade-offs, mechanical complexity versus potential efficiency gains with Transwing, and seeing how fast battery tech keeps improving. How will the future of VTOL powertrains shake out, especially for these heavy lift jobs? Could we see totally different approaches emerge to crack that code of vertical flight combined with efficient long-range travel? Definitely some food for thought. Thanks for joining me for this deep dive.